My name?
Yeah.
It's Yannis. I don't know if you can call it Yannis, like the NBA player.
Yeah.
Yeah, it's the same. Or John, or there are so many different names. Yeah, right. Yannis. Wait, how can I do this one? Can you help? Okay, no, like this. Okay. Okay, now I see. No, no, this one is pointed. How can? Okay, it's. Give me one. Uh, okay. Can I start? Okay, I'm ready. So, hello everyone. My name is Yannis. I'm a second year PhD student in electrical and computer engineering at Yale. I'm working with Professor Leandros Staskioulas, and we are affiliated with the Institute of Network Science at Yale. So, just a brief overview about our group, what we are doing. So, we have different threads. The first one is why we are interested in next generation networks, software-defined networking and no-RAN. Also, we are interested in security and IoT and wireless devices. And mostly, most of the PhD students they are working in AI. And also, we are interested in quantum communication networks and finally in blockchain. So regarding me, I'm more interested in next generation networks, AI, and LLMs. So regarding me, the main research threads that I am actually interested are the following. So first of all, I'm the leader of deploying our own 5G testbed in the lab. So we have a 5G small scale testbed, and we're utilizing SRS Run and OAI. So Babran is actually a startup in France. And we want this testbed for over-the-air testing, data collection, experimentation, and closed-loop control of the run with AI machine learning algorithms. So regarding me, I'm working on these 4 different tasks. The first one is we want to develop algorithms for intra and inter-slice handover. So, for example, you have multiple UEs that are connected to specific slice. So you have multiple slices in base stations, and you want somehow to understand how you will switch a UE from a slice to another one, based, for example, from the not load or based on the security policies of the slice, etc. So right now we are developing a deep reinforcement learning agent that uses the state of different slices, and based on the state of the slice, it will decide where the UE will connect. So a different project that I'm working on is run slicing using hierarchical reinforcement learning, as you can see here. So you have like an agent in the non-real-time recontroller that actually specifies how the resources will be allocated. For example, you have different type of resources of PRBs. You have like prioritized resources, or maybe you have shared or dedicated PRBs for specific slice, and then it will give the policy to the near real-time controller where you have a different reinforcement learning agent, and there the agent actually will decide how it will allocate the PRBs to a specific slice. So maybe you have like 3 slices, an EMB slice or ERLC, and the agent will decide like how you will allocate these resources. So the third one is that actually in this month we will publish we will release our own telecom LLM. So we have trained it in around like 5 terabytes data. So we have downloaded all the archive with all the different telecommunication papers. So we have downloaded all the 3GPP documentations, and we have trained our LLM using 8 GPUs A100. So now we're just considering different use cases for our LLM. For example, one case is RF fingerprinting. So you have some data, and yeah, of course. 1 minute, okay. So you have different data, and you just feed it to the LLM, and the LLM will decide what, for example, in which if it is like a macro cell or a different cell. And finally, like I'm also interested in working in limited software-defined synchronization algorithms. For example, you have different SDN domains, or each controllers actually, receive some domain state information from domain, And so you want to to implement a reinforcement learning agent that will receive data from its domain. But the main idea here is that you want to minimize the control plane messages that are exchanged between the controllers. So the main idea is again like like compression of the control plane messages, but without violating the SLAs between the slices. Uh, that's it. Thank you. Any questions? Yep.
So what is the main benefit of LLM, that large language model, compared to, let's say, convolutional neural network or something?
So the main difference.
Yeah, main benefit, yeah.
So first of all, you can use it for education. For example, let's say that you want to learn more about telecommunication, right? You can use our own LLM, so it's trained on all the data from the telecommunication, so you can learn more about, like, let's say, telecommunication. A second maybe use case is like you want to use it for, well, let's say that you have a file that contains data from some RF measurements, and you want somehow to understand if these if these measurements are from, a macro cell or from an urban cell. I don't know. So there are a lot of different use cases that you can use like the LLM.
So it is more for text processing,
Yeah, it's more for text,
not numerical.
but still it's
They can do it.
yeah, I think also you can use it for numerical. Yeah. Okay, thank you.
Thank you. Sorry. Okay. Okay. Hello all. My name is Sonali Chaudhary and I am a PhD student in Computer Science Department in North Carolina State University, and my supervisor is Dr. Rudra Datta. So my primary research is for UAV trajectory planning, where I'm focusing on adaptive applications. So adaptive UAV applications are those which can adjust their transmission based on varying radio conditions. So my background is like I'm from software background, so I'm not very well aware of the signal processing and wireless technologies. So my primary work is on the algorithms. But to test those algorithms, I have to look into the cellular network, the 3GPP models that I simulate and I work on to verify the performance of the different algorithms which are in the literature and for my algorithms as well. So in that process, I have started exploring the cellular network and literature around it, and ORAN literature and understanding of how these things work together and how it can be used for the UAVs and ultimately for their trajectory planning. So I am here for the workshop, and so along with the trajectory planning, I am exploring how ORAN can be used and enhance the performance of or the coverage for UAV and in the trajectory planning. So these are my like different branches that I'm working on for my PhD. But along with that, I am also working as a research assistant in the airport test bed. Some of you might know it is a test bed similar like wireless test bed in the NC state. So there I started with participating in one challenge, which was Find a Rover challenge, where I collaborated with some PhD students in the EC department, where the idea was to use a UAV and find a rover which was placed in the ground. So my role was to develop the application layer, and like is a student, a PhD student from EC department, he worked on the wireless signal processing. And there is one another experiment I'm working on is which is the petal routing, where I'm verifying. So idea is to have multiple UAVs in the ground, and they will have a limited range where one UAV will send a message to some another UAV, and intermediate UAVs will transmit it. So idea is to implement the algorithm or design algorithm where we can efficiently forward the messages. Yeah, so like these are the various pointers where I am working for my PhD. Thank you. Any questions?
So you have this trajectory planning.
Yeah.
So do you try to avoid some obstacles or something?
No, it's
Yeah.
only regarding the coverage where, yeah, UAV will try to be in some coverage points and, yeah, ignore the coverage holes. Yeah.
So basically, your cost function that you're trying to optimize is the cover.
Yeah. The idea is to optimize the distance, like distance should be the minimum and coverage should be maximum, you can say.
Coverage of what? Cellular coverage?
Yeah, cellular coverage that UAV gets. Yeah. Okay. Thanks. Thank you.
Okay. Hello, everybody. My name is Hassan Ali. I did my PhD from University of Malaya. Currently, I'm working as an assistant professor in Southeast Missouri State University. Initially, I start my research in wireless sensor network in my PhD, and later on, I realized that the sensor network have issues with the energy and like routing the data from one place to another one, and the computation, especially and the sensor node side, is huge, and the nodes are very tiny, so they cannot manage the computation. Then I realized that we can establish like the data with the sorry, we can connect this sensor data with the cloud to to take the advantage of cloud computing and make a new paradigm like sensor cloud. So mainly sensor cloud is the combination of sensor network and cloud computing. Like there is some challenges in sensor network, as mentioned, like the sensor cloud provide scalability and storage and high performance computing, which we are facing in sensor network side. So when we are using cloud computing, integrating cloud compute cloud computing with the sensor network, it gives us the scalability in storage and computation and real-time data processing and storage. So these are the advantage of using cloud computing with the sensor network. And then there is an issue like if we are uploading the data from sensor network side, it will be mean if it is like real-time data and time-sensitive data, it need to be processed quickly. Instead, like if we are uploading, definitely there will be a delay in uploading the data. Like for example, let's suppose the patient data. The patient data is uploading to the cloud, and then the doctor remotely watch the data. So if his blood pressure is high, maybe when the doctor wants to see the data, he will be dying. So we need to find a solution for that as well. That if like sensitive data, how we can handle that data. So we use the edge computing layer inside the sensor cloud. This is general architecture of sensor cloud, but we use the edge layer to process the sensitive data on the edge layer. And if we are not like the data is not sensitive, we can upload to the cloud. And from the cloud, we process the data, and later on, the user can use anytime their data to to deal with their own responsibility. So this is just a new framework like intelligent zero touch data collection framework in sensor cloud. In this framework, we take the data from sensor network, sensor layer, and then we see that if the data is urgent data or sensitive data, we process it on the edge layer. Like there is a edge layer and there is a cloud layer, and there is a user layer in the top. So we process the data that is sensitive data. We process on the edge layer. If it is non-sensitive, we have to upload to the cloud. Like cloud is not like the important data is not that we can process on the edge. So we keep it in the cloud, and the cloud will process the data, and the end user can access that data anytime. So the main idea is to using zero touch. So in this framework, we will be using like AI to process the data, and we are getting some data, and then we can do prediction as well. That if we have some constant data coming, and we know that we don't need to get this data more. This data is coming. If there is any new change in the data, then we can take the data. So we will use that pattern discovery in the data, and then they generate new message that we need more data or not. So in this type of framework, we process the urgent data on the edge layer and non-urgent data on the cloud layer, and the user can access the data from the cloud anytime and from the edge as well. So this is just a general overview of my research. If someone have question, we can discuss idea. I have some ideas to work on it and submit a grant for NSF. Thank you. Any question, please?
Have you run simulations or you have some prototype?
Yeah, this is some prototype, like theoretical things, not practical. In Malaysia, there are no resources to run like practical things. So mostly this is theoretical perspective, and I'm here trying to get some grant and hire more students to run some practical lab things. Yes, please.
So in the report, you have the capability to upload the data with the sensors to the cloud. So why do you process them in the
No, there will be a gateway. Like on the edge layer, there will be a gateway in the sensor device side. The gateway will be upload the data, not the sensor node, because the sensor node are not that uh, energy efficient. So they upload to local gateway, and the gateway upload the data to the cloud or the edge computing. Thank you. Any question, please? Thank you.
Really quick, sorry. So I don't have to keep saying it. I've been delegated the task of marking time, so I'll just let everybody go and know who's got 1 minute left. Keep an eye on you. Thank you. I'm still working on it.
I'll put it in this one. Should I talk?
Yeah.
Click on it. Okay. Hey everyone. My name is Leon Eifer. I'm a PhD student, first year, enrolled in University of Michigan Dearborn. I work with Professor Junaid Farouk, and I'm currently working on network slicing, specifically in resilience, how to recover from cascading failures. Uh, so I'm basically working on the control plane, how to perform network slicing in that area. Basically, uh, the main problem is how to formulate it in a MILP problem and how to solve it so that you can know how to place the slices on a physical substrate. For those who don't know what network slicing is basically how to divide a physical substrate into multiple virtual networks. They are all hosted on the same infrastructure. Um, the type of slices I'm focusing on are the URLLC and EMBB and MMTC. I'm working on 5G networks specifically. Um, every slice has to meet the necessary requirements provided by the users. You have to make sure that we do not violate any SLAs, service level agreements, and basically, this is, for example, one example how we can divide a physical substrate into multiple different slices. my main focus is basically how to make sure that we uh, push forward and take security and isolation between different tenants to the next level. Make sure that there's no violation of any kind of um, uh, failures. Um, the benefits of network slicing is basically we guarantee performance for every users. We maximize the security. We focus also on the scalability and flexibility, and while minimizing the cost. Um, what I'm currently working on is DDoS attacks. I'm trying to simulate DDoS attacks in within 5G networks, trying to measure how by flooding resources we don't we deny they deny the users or the other slices resources, which is terrible for user experience. And I'm trying to figure out a way how to make the system resilient and robust against these types of attacks. Sorry. So, any questions? So, when you have like DDoS attacks, is like you focus on one node, for example, and then you try to infect the other nodes, the neighboring nodes. You can think of it as a connected servers, and if you basically attack one server and you infiltrate them, you can jump into the nearby servers and you get control over it. And that way you can um, consume their resources, thus uh, um, making the other slices, thus the other slices don't have enough access for their own resources. That's what we're currently focusing on. Uh, any other questions? I don't know if I answered your question. Yeah. The main objective is to maximize the isolation between the slices. Like for example, if you attack one slice, you mitigate the effects on the other slices. So basically, you maximize the isolation between slices, so that if one user is attacked, there's no need to affect the other users. At least try to minimize it and make it focused on one slice, then focus on it recovering on its own. Yeah. Yeah, that's why we're trying to figure out some kind of um, for example, RL agents that can find the best and optimal solution to embed or to map the slices on a physical substrate. Because using traditional approaches like MILP problems, it takes a lot of time. So we're thinking of who knows, maybe LLMs can figure it out in the future. And RL, man, federated learning, I'll, maybe, yeah. Thank you.
But usually you know the location with respect to GLOP of whoever is trying to attack you, right?
Yeah, but we're assuming that the attack already happened and some slices have been already been compromised. And in that case, how can we mitigate the effects? We don't let it propagate any further. So that's the objective. Like nobody can um, make a secure system against all types of attacks. That's not a guarantee. So in case of failure, what can we do to make our system keep on working? And that's how we define resiliency and robustness. Thank you.
Hello, everyone. My name is Adwa. I'm from Rutgers University. I'm a researcher at the CPS lab, which is the Cyber Physical System lab. My supervisor is Professor Dario Pompili. I'm working in the electrical and computer engineering department, and I'm a researcher too, working in the ORAN and machine learning. My major is computer engineering, and I'm trying to to build a complete test bed for our lab. So that's why brought me here. Okay. Okay. So our major work in our lab is about the Cloud RAN first. We started building our Cloud RAN, which is centralized RAN processing where we trying to make the heavy load on the cloud while we try to process the light process the right radio connections that that needs right like less centralizing. We're gonna make it next to the radio connections. And here we have to the mobile edge computing, where we try to bring also the resources next to the user. So this is gonna make it less and significantly gonna reduce the latency, because the user can have the resources next to the edge computer. And here then we're gonna started to our research to do the next generation RAN, where it's offering the flexibility and make us have the traffic management and also low latency, because we're having the near real time and real time, and also the real time, the non-real time rigs controller. And now we're trying to build the near real time rigs with the microservices, so we can control these subject that we have here. And here we have the Cloud RAN, where we try to support the virtualization, because it helps us to do the BBUs, where it has all the heavy computation, while we have the head radios have the light computations. That's going to reduce the latency and make efficient resource allocations, and also less CPU consumptions. And here we implemented our testbed in our lab. This is very low scale testbed where we have the Open RAN interface, the OAI in our computers, and we use the USB 210 in our lab to communicate with the codes, which is the Galaxy 2S. This is the main scale, the very small scale testbed. And now we're trying to scale it up and try to build a larger testbed where we can include the multi-services in this small services, the X apps and R apps and D apps into our RAN and small testbed, so we can control it, and also to provide near real-time controller into our X app, into our ORAN. And also we're searching the ability to disaggregate these X apps, so we can try get efficient X app controlling into our ORAN and see how many X apps we can include in this ORAN, and if it's efficient to have like million X apps that control this ORAN. So this is the main project that we're working on. Yes. Yeah, oh, 1 minute. Okay. So this is the main ORAN project that we're working on now, and trying to scale it up and see how many X apps that could control the ORAN, and trying to build the near real-time controller. If anyone has a question here. Any questions? Really good. Okay.
So I'm seeing.
This is our mini small-scale ORAN in our lab.
So I'm seeing in your diagram you have eNode B.
Yes.
VPC.
This is the OpenAI. Yeah.
Okay. So are you doing? So is that just strictly LTE that you're doing, or are you looking into like 5G as well?
Yeah. We're we're planning to build the core 5G network and trying to communicate it with the codes or another kind of UEs in our lab. Yeah. Yep. Yep. Yes, three.
With the different
Yes.
radio?
Yeah, we're trying to use the 3B300, and also we're trying to change the UEs into another USRB so we can make traffic between these two. Yeah.
How do you use the microphone?
Hello everyone. So my name is Raju. I'm doing my masters in University of Louisville. I'm in my final semester, and so okay. So like my now I'm gonna explain about my paper. So my paper is about what?
Present.
Automatic. Let's try.
So the research is about closed loop tele-robotics over software-defined radio-based wireless testbed. So the main motivation is to use the 5G infrastructure with tele-robotics. Basically, tele-robotics is like controlling any robot remotely, or which can be wired or wireless. So in wireless, we are trying to employ 5G architecture and see the displacement or noise to ratio or such kind of parameters. And for this kind of applications, we need high speed communication, and 5G comes correctly to the picture. And so in telerobotics, challenges are like the signal strength plays a vital role. Like if you have like weak signal ratio, there will be a loss of data and robot operates wrongly. And so while coming into the experiment system overview, so basically what we are doing is like we are taking two systems. One system is for the robot. In that system, we are kind of like installing the simulator version of a robot using ROS, and another system does the commands. Like it can be operated by a person, like giving commands to the robot, and the other simulator version robots perform the task. Like in the system one, you can control the robot in the system two. So can I play a video, YouTube video? Um, here is the link. Where is the mouse? Yeah. Where? Yeah. Right here. Can you? Oh, it's not. Oh, I can explain over using picture. So basically, as you are seeing, we are using SRS RAN for the 5G and UE as well. So we are using SMA cable to transmit the signals, and we are using two USRP B200 radios. So if you see, this is the laptop which send commands, and this laptop has the simulator version of an robot by ROS. And in this communication, we have set a few default positions to a robot. For example, position A to pick an object, position B to place an object. Like that, we have taken like 7 to 8 different positions. So here we kind of like sending those positions rapidly and seeing the parameters like communication delay, displacement delay, etc. And after that, when the robot is performing the task, we are also sending the video of the performance to the transmitter as well, which makes it closed loop. And these are the results which we observed. And as I mentioned previously, we have fixated 5 tasks. These are the 5 positions which name them. And these are the results which we found. Basically, we are observing the parameters of the 5G. For example, here you can see uplink and downlink and signal to noise ratio. And these are the parameters which we can find in SRS RAN. So while the main problem which we mainly faced is while setuping in the SRS RAN, we got so many configuration related to issues, and we took our time to resolve it. And after that, we observed one more problem is that when we send a continuous bit rate up to like 2 or 3 minutes, the signal got overloaded and breaks down. And these are the few limitations we found it. And at now the experiment is fixated on a simulator version. Our main goal is to like operate a real-time robot using our transmitter. Thank you.
Are you doing position control or force control?
Basically, in the simulation, we can only like do a position control. So what our main intention is to like operate the robot itself. For example, if you are at a transmitter end and at the receiver end, if you consider a drone, you should operate that drone like that. For in simulation, we don't have much scope, so we are kind of fixed some positions to the robot and we are operating remotely.
Thank you.
Ayanta?
Hello, everyone. So I am Shanto, and I'm a postdoc at the NextG lab at the North Carolina State University. And our group, led by Dr. Vijay Shah and students Abhyodin and Pranshab, we are working on AI-assisted ORAN testing and privacy vulnerabilities. Although our group is has been working for a long time on ORAN, I am actually new in this field, so that's why I'm attending this workshop. So when we're talking about the main motivation, so the ORAN Alliance Working Group, they have documented various test cases for interoperability and end-to-end testing. So when we say interoperability, it is like the seamless working between the various disaggregated RAN components, and it is very important because the ORAN Alliance has said that we can have various components from various vendors, and they must be working seamlessly all together. And there are also documents which are used by 3GPP specifications. And the current process when we are doing interoperability testing is a manual process where we capture packets from the 5G network and check if all these signaling messages conform to the specific 3GPP standards. And the problem with this manual approach is that it is time consuming and it is obviously prone to human errors. So the solution is that our lab is addressing this challenge by developing an AI-assisted testing framework. And we aim to automate this process of validation of signaling messages and control plane messages for improving the efficiency and accuracy of this testing. Apart from this, we are also working towards investigating and testing the privacy and security vulnerabilities of the various Open RAN interfaces. So if we are talking about various components of the testing framework that we are developing, the first is the database, and its purpose is to host and manage various test cases. And the main function of the database is to store the test cases related to the metadata and to retrieve these test cases for execution. And the another component is packet or the log capture, and this is used to capture the logs from the ORAN components such as the CU, the OpenCU, and the DU. And the functionality of this packet or log capture is the integration of this capture tool to analyze the captured packets. Also, we are developing an user interface or an UI, which will provide a user-friendly interface for this test case selection. So we may have a list of test cases, and we can select a specific subset of these test cases from that user interface. And the test engine will be used obviously to execute these test cases and validate the signaling messages against 3GPP specifications. The purpose of the LLM tool will be to understand and interpret these 3GPP specifications. Now, when it comes to the ORAN security and privacy vulnerabilities, for example, in the F1 interface, the security vulnerabilities are the data interception and data manipulation. For example, when we are talking about the user plane data, if it is not adequately encrypted, it can be intercepted, right? Also, when we are talking about data manipulation, that means unauthorized modification of the user plane data, and that can lead to corruption. When we're talking about the XN interface, there are vulnerabilities for handover data exposure. In the open front haul interface, we can have like the vulnerabilities could be data interception again, data integrity, and tracking and surveillance of IMSI or SUPI. There could also be impersonation attacks, fake base station attacks, and unauthorized access. So these are some of the privacy and security vulnerabilities that we are looking into at the Next G Wireless Lab. So these are some of the live packet capture analysis testing that we have done using both SRS RAN and OpenAI, and it works it works works well with both SRS RAN and OpenAI. And we have also automated the Wireshark signal message validation. We can also show the initial. So when we were running the base station, it's done. Oh, sorry. So I'm almost at the end. Um, in summary, we are planning to testing out the penetration testing methods on the OpenDU. We're also testing sensitive data in the RLC stack. We are testing the various entry points to accept, like the A1, O1, E2, and the A2 interfaces. We're also testing out the privacy vulnerabilities in the E2 termination node. And yeah, that's a brief overview of our work.
Any questions? Will you consider the 3GPP conformance test for your ORAN?
Yes, that the goal is to have all the 3GPP documents that are there, and we are trying to develop a user interface using LLM, so that it becomes very easy to do any sort of conformance testing and interoperability testing. So we are trying to automate this entire process.
Thank you. Anything.
Oh, can you guys hear me? Great. All right. Hey guys, my name is Dimitri DeSuze. I work at Wireless at VT at Virginia Tech, and my advisor is Dr. Jeff Reed, and I also work very closely with Dr. Tripathi here. And my current research for my PhD program is holistic cybersecurity and 5G ORAN threat, not thread, threat modeling, and also threat mitigation as well. So as we know, vulnerabilities are very common, as we just heard, in a lot of these networks, due to either just coding discrepancies or standard discrepancies. This leaves avenues for vulnerabilities to arise in a lot of networks, especially legacy networks, and they have persisted up into our current networks and are expected to persist into future networks. So common vulnerabilities and exploits, including downgrading attacks, replaying attacks, IMSI and SUSI, however you say it, however you want to say it, catching, and spoofing and identity disclosure. So there's a lot of different potential results due to these attacks and potential implications for the security of 5G. So things like taking identity from people, a lot of things that probably most of us have experienced ourselves, just kind of random, cold calls from people claiming that you owe the government $9 million or something like that. These people who get your access do so through these exploits and vulnerabilities. So it is very important for us to examine these avenues which people can get in and hopefully close them. So one of the avenues that we're closely looking at here are exposed clear access and non-access stratum signaling messages. So if you were to take a look at the initial registration process of 5G, you'll notice that the security of access and non-access stratum happens well after a lot of the RRC and NAS signaling messages, the initial NAS signaling messages. So it's important to keep these things open just for the sake of a very easy connection process, but since they are transmitted in the clear text, anybody with a little bit of savvy and some, commercial off-the-shelf technology can just capture your messages and perform these attacks. So we want to examine how can we improve the security of these open clear text messages without compromising the performance of the network. So first we take a look at what are some of these things that cause these vulnerabilities in 5G, and how would the integration of ORAN interfaces exacerbate or expand those threat surfaces. So as you can see here, this is a diagram, just a typical diagram of the ORAN interface. We have in red the ORAN interfaces that are being integrated, and then 3GPP maintained interfaces as well. So for example, as you can see, we have the O1 interface connects to just about every other function block except for the RU. So that kind of suggests that if an adversary or any malicious entity were to get control of this O1 interface, they could do a lot of damage. So things like this where we see, okay, this is an example of how the expansion of the network could lead to possible vulnerabilities. So we're interested in testing what are some of these attacks that they can do through these avenues, and again, how do we make sure that it is a bit more secure. So some of the things that we are trying to take a look at in terms of determining how these vulnerabilities arise is fuzz testing. So fuzz testing is somewhat of a form of stress or penetration testing where you just generate a lot of edge cases or cases that are aimed to break the network. So we introduce some malformed packets. So specifically in this case, we would talk about malforming RRC and these initial NAS registration packets, sending them into a network, receiving them on the Gnode B side, and seeing how there is any kind of performance degradation at all. And again, as we continue to do that, the idea is to let software developers know of these issues that arise, and from that as well, we can maybe even come up with some methods, either through the deployment of XApps in the future, just better coding algorithms, or better standards and policy to mitigate, again, these attacks. So that's about it. So are there any questions? Great. All right. Well, thank you.
Hi everyone. My name is Siddharth. I'm from University at Buffalo. My advisor is Dr. Zhang Yuguan. So I'll briefly touch upon two of my research topics. So first is wireless sensing, communication, and networking for advanced air mobility. So I work on developing the interference resilient protocols. I work on mostly the signal processing side of things. So one thing we do, we are a very hands-on team. So we have a drone team where we are developing these heavy-duty drones that could lift up to like 70, even 30 to 40 pounds of payload. So whatever the signal processing algorithms or whatever we develop, we mount this payload on the drones, and we do a lot of we do a lot of outdoor testing. We have a outdoor facility in our university where we do the swarm testing. Another research that is worth mentioning is experimentation and softwareization for future wireless networks. So we are developing this infrastructure. We call it Union Labs. So in the research community, one end of the spectrum, we have these researchers who doesn't have access to expensive hardware and software resources, and at the other end of the spectrum, we have researchers where their test beds are underutilized. So we are trying to bridge the gap between these two by providing an infrastructure to enhance collaboration in the research community. So you can think of it as like a GitHub for testbed. It's we are trying to making it as intuitive as possible. So you can think of it as a GitHub for testbed, or even an Amazon shopping cart where you can just go to the portal and just try different test beds across different universities. So we are already collaborating with the University of Utah So they have integrated their IoT testbed into our platform. Yeah, that's it pretty much. Thank you.
Using 4G, 5G, what kind of
Uh, yeah, so the the main it can be anything basically, but the main focus of the research is to provide an infrastructure. So we have integrated an ORAN testbed in our university. We also have integrated an underground and underwater testbed, but I mean it's an small it's like a sandbag, like it's a small emulated environment. But we have also integrated an IoT testbed with the University of Utah. So
you are in the air,
yeah.
underground, and underwater. Amazing.
Yeah.
Yeah,
Yeah.
you just need to go to space and you complete.
Yeah. Thank you.
Yanzi? Does it have some? It's just for Zoom.
It works.
Oh, it's for Zoom.
Yeah, it's for Zoom.
Okay. Uh, Hi, my name is Yanzi Lee. I'm a PhD student from Northwestern University, and I forgot to add my advisor here. My advisor is Iko Katona, and my general research interest is to uh, design using the traditional way, the information theory, or the newly machine learning based way to design network control algorithm. And my focus is to do the implementation part to design systems that could like to apply those algorithms. And the reason I come to this workshop is to I want to learn to develop the test beds that we could use to evaluate those systems and the algorithms. And I learned a lot today. Thank you very much. And the research I would like to talk about today is um, we is predictive network slicing admission control in wireless networks. So the network slice, the concept of network slice has been introduced by the previous slide, so I won't mention here. And this research, like we have three um, uh, assumptions here. Is that first, uh, we assume that like this is a common circumstance that the network capacity of a link could drops or change during different circumstances, like there's a rain, there's a snow, and previous study usually assume the for admission control for network slice assumes that the capacity is stable, but here we would like to consider that the capacity could change. The second is like we have various network types of network slices, and they have different demand and the cost of accept these different types of slice is different. And the goal of this research is that under where changing network capacity, how to maximize the rewards for infrastructure owners to determine what network slices to accept for admission control. And that leads to two goals. So first, we want to design an algorithm that could predict future attenuation levels of each link. That is, we want to predict how the network capacity of a link will change in near future. And second, we want to apply these predictions to perform admission control of incoming network slices such that it could maximize the revenue for infrastructure owners. How to move to the next? And here we are still at a stage that we design some algorithms for admission control, and we will use a data-driven way to simulate how different algorithms perform to generate the rewards. For example, like if we have a baseline there, if that we admit all slices regardless of the that's in simulation regardless of the capacity, and we have greedy avoid drop. That means like when the capacity uh, we will never have avoid the circumstance that where the extreme circumstance that the capacity drops such that we have to drop some of the slices. We want to avoid those extreme cases.
About 1 minute.
Okay. Yeah. And here we have some like preliminary measurement in the simulations, and we would like to develop more algorithms. Especially we still haven't to incorporate the capacity prediction part into our admission control algorithm, and that's our goal in the future. Thank you very much. Any questions?
So right now you are considering 3 slices.
No, just two slides.
Two.
Yeah.
Which
Also, sorry.
network slices you say you are considering
Oh.
the triangle.
Oh, so
there are 3, right?
yeah. This is I just use an example and
Example.
yeah, and for simple at least and for simplicity in our current simulation, we also consider we only consider 3 types of slices. They have different rewards and they have different penalty when you have to drop them. But definitely reality, we definitely could have more types of slices, but the idea is the same, and we can increase the scale of this simulation and experiments to test for more types of slices.
And what kinds of resources do you look at?
Only the capacity.
How do you quantify capacity? Some resource blocks or something?
Currently, we only consider about throughput. Yeah.
Have you thought about considering things like the establishment costs, like you mentioned, establishment costs, or
No, we just assume the infrastructure is there, but how the infrastructure owners could decide whether they to accept new slices when the request coming, especially they have the prediction in mind. If my capacity is very likely to drop in the near future, then I should be more conservative to accept new slices. Otherwise, I will incur penalty. Yes, please. The prediction here, we currently have 2 types of prediction in mind. The first is that the first algorithm is that it it tries to estimate an overall conservative degree for the link, and such that based on this all the overall conservatives, we adjust our admission control strategy whether we should be more greedy, aggressive, or be more conservative. The second types of prediction is that we want to generate capacity possibility, a list of capacity possibilities such that like we have 40% of possibility that we will get this A capacity in this time, and we use that to adjust our admission control strategy. Any other questions? Thank you very much.
Adireza?
Hello, everyone. My name is Ali Reza. I'm a first-year PhD student at Clemson University. I work in ISVN lab under supervision of Dr. Fatima Afka. And my main focus on research is task offloading on multi-access edge computing servers. So the problem that we are facing right now is that there are increased number of connected devices that would cause network congestion and pressure over the backhaul of the network. It will actually increase the latency to get the results back, and it will definitely increase the energy consumption. So the 5G, on the other hand, proposes opposite of that. So it promises enhanced data rates, reduced latency, energy saving, and cost reduction. So in order to tackle this problem of increased connected users, and on the other hand, the energy consumption of the IoT devices that are going to be connected, we can use edge computing. It will allow for data to be processed closer to the source of generation of that task, instead of being transmitted to a central server, a data center, to be processed over there. And this will actually reduces the amount of time and the data that needs to be transmitted uh, to the central servers to be processed. So the multi-access edge computing, or MEC, is a network architecture that enables the edge computing. It allows for the data to be processed and stored closer to the end user or the source of the generation of that task. It will definitely improve the latency, reduce network congestion, and provide a better overall user experience. In order to do the task offloading, what we will need is the computational resource for processing the task and the communicational resource for offloading the data from the source to the edge, server that we are going to process that data. So both of these resources are kind of limited. So we're going to need a controller in order to decide which task should be offloaded to the server to be processed, and how much resource, both computational and communicational resource, has to be assigned to each one of those tasks. So my research right now is to find a real-time controller to be deployed in the X app to decide whether to decide which task should be offloaded to the server for processing, and how much resources, both communicational and computational, should be assigned to each one of those tasks. That's overall of my research. So if there is any kind of question I can answer. Or... Yes.
Regarding that, you mentioned that you are using edge server. Only edge server, one edge server, or there are more edge servers? And how much area you are covering, like the data, sensor node that you deploy IoT devices?
So the architecture that 5G proposes, the multi-access edge computing. So you can use the make servers in each part of those DU or CU, depending on how you formulate the problem. So there are some powerful servers connected to maybe even the RU or the base station for processing the data. But you might have more than one server to process the data.
Yeah, but there will be task assignment issue, that how you can assign the task from which server will be processing that data.
Gotcha. Okay, so so the task request consists of a tuple of how many CPU cycles that task need, how many bytes to be offloaded, and the latency or the age of information to process that task. So based on that, the intelligent controller is going to decide, and based on the amount of overload on each one of those servers, that intelligent controller is going to decide this task should be processed in which one of those servers.
Yeah, that's a good solution, but like in case of emergency, like you need to process the data quickly, and there is another server that's busy. Mm-hmm. So how you handle that type of situation?
So the other architecture that you can kind of use is to use both Cloud and then the make servers. So the make servers are pretty close to the source of generating the data, and they can process some of those tasks. But if they are kind of overloaded, you can send the data to the cloud.
Compute-intensive data will be uploaded to the cloud.
Yes. Yes.
How will you solve such problems? Like which server to assign to, how much resources to allocate, and which one to offload?
Okay. So as I said, each task consists of a tuple. Each task request consists of a tuple. The first one is how many CPU cycles that's going to need. And the second one is the latency that, the second one is the bytes of data that needs to be offloaded in order to process that task. And the third one is the latency that is required. So in order to avoid the SLA violations, you have to respect that latency. So that intelligent controller is going to decide based on the knowledge that it has from the resource blocks on each one of those servers and the computational power that each UE has. This task should be either processed locally, offloaded to one of those make servers, or be offloaded to the cloud server.
How would it take the decision, like this intelligent controller?
Oh, so you mean the deploying of? How?
What kind of algorithm are you using?
Oh, we are using RL agent, reinforcement learning.
How would you measure the reward?
So the reward is, it kind of, it depends on what you're gonna minimize or what you're gonna maximize. So in order to minimize the SLA violation, because the task need to respect the latency of latency to be processed, in order to decrease the SLA violation, this is one of the cost function that you can use. The other one is the power that you're going to use, because these are mostly IoT devices that are going to be uh, scattered around the area that is going to process the data. So if you are going to process it locally, it consumes this amount of energy. If you're going to offload it to the make server, this is going to consume another amount of energy. So that RL agent it's pretty much flexible based on what you define as a cost function. But these are two of this basic, yeah.
So that's like you're talking about the real time scheduling, but you're talking about the each side. Usually you said are working at the near real time. And near real time. How we want to add to the real time?
The R app was near real time, right? This is real time. XF is real time.
That is near real time.
Oh, I'm so sorry. Yeah, that's it. Okay, that's a mistake.
Yeah, the real time is called EAD.
So
It's
consider
just-
this
it's
near
just
real
a-
time,
just a-
not the orange
just a
real time.
limitation.
That is what
It's
real.
okay. It's just
Yeah.
a limitation. Don't worry. Any other questions not related to naming issue? Thank you so much.
Hi everyone, my name is Rajendra Upadhyay and I am PhD student at George Mason University under Dr. Juminda Vaijasekera. So I joined as a PhD student in last spring. So it's about like 6 or 7 months. So basically I'm the student of information technology in cybersecurity concentration, and I'm currently working on like providing technical and research assistance regarding the open source softwares in providing cybersecurity solutions to a company from our lab. So I basically worked in like software related to cybersecurity that are like OSSIM Security Union, that's in the domain of passive SOC, and we also worked in the like CSOT domain and homologous domain. And besides this, I'm currently working on like integration and comparison of different available 5G core networks. And as you might have already known that there are various open source 5G core network like Open 5Gs, Free 5GC, OAI, and Magma. So for this work, I have chosen like two 5G core networks for exploring how they work and find out which of the open source 5G core network is efficient. So for this part, we choose like Magma and OAI open source 5G core network. So the objectives was to just to establish the initial test bed for the end-to-end deployment and compare the performance of Magma and OpenAir interface 5G, and to integrate both the network is also the objectives of this project. And as you can see here that there are architectures related to Magma architecture and OAI architecture. Magma is actually founded by Facebook in I forgot the date, like in 2019, and later it is gone. Now it is governed by Linux Foundation Network. And what caught the attention to explore the Magma architecture is it's non-compliant with the 3GPP. Like other 5G core networks are compliant with 3GPP, but Magma is non-compliant with 3GPP. Um, uh, but in the core part only, but not in the interface. I mean RAN part. In the RAN part, it is compliant with 3GPP, and in the Federation Gateway part also it is compliant with 3GPP. But in the inside the core network elements, it does not comply with the 3GPP protocols. So we try to explore that. And OAI architecture, I think most of you have already been familiar with the OAI core architecture. So this was the test bed used for the work. So as you can see, there are three elements in the Magma core architecture. So that was like NMS, an orchestrator, Magma access gateway. They call the core architecture as the access gateway. And there is another optional components of Magma 5G architecture, that is Federation Gateway. And for this setup, we used 4 machines, each representing UE, RAN, core, and the orchestrator. And for OAI testbed, we used 2 machines, so RAN and core in the one machine, and the UE in another machine. So for the integration part, we implemented we want to implement the Federation Gateway in between the OAI and the Magma core. So works so far. So far we have deployed like Dockerized Magma 5G core component, tested it with the UE ransom in simulator and USRPs. And in regarding 5G OAI core, so we deployed OAI 5G core, ran and UE, and tested with USRPs currently. So in future, we want to deploy the Federation Gateway. That's the important component of the Magma architecture, and compare. We will evaluate the performance of both the Magma and OAI 5G testbed and integrate them. So my research interest is, so basically whole semester I worked in like cybersecurity domain, so providing open source security software related to open source security software. And so as a future career, future research, I wanted to work in the ORAN domain, which is the interaction of machine learning and wireless communication. So that's why I registered for this workshop. And so yeah, I think it will provide me with the opportunity necessary.
So when you compare these two core networks, right, what kind of performance?
No, I mean, we wanted to compare. So lately we started this project, so wanted to compare the currently we are in the deployment stage. So some part of components are deployed and some parts are remaining. So it is the future.
Okay.
And when you say Magma is non-3GPP compliant, what does it mean?
Yeah, it means that so in OAI you might have seen like bottleneck functions like UPF, AMF, SMS, so something like that. So in the case of Magma, that is not the case. So they implemented the functions but with the different I mean components, not as defined by 3GPP. So on the RAN side, they can work with any RAN components, but inside their core architecture, their components are designed in such a way that they are not compliant, or do not follow the 3GPP protocols.
Does it require less resources?
Yeah, it is lightweight. So basically, Magma Access Gateway is deployed near the base stations. So it is lightweight and it functions as a fully core component.
Who developed it?
Facebook, and currently governed by Linux Foundation. So thank you.
is there a clicker? No, okay. Cool. Cool. So my name is Robert Hayek. I'm a graduate student at Northwestern University, and I'm working with Argonne National Labs to develop a 5G testbed for science use cases. So there is a collaboration between the Department of Energy National Labs, the main two being Argonne and Berkeley, which is working with Los Alamos, to develop a multi-lab shared 5G capability for the DOE complexes. And basically the goal is to create some sort of EDU roam, like we have with Wi-Fi, but with 5G cellular for use with sensor networks, nodes, edge communications with large server complexes, or distributed networks. Mainly, this is to just ease scientific deployment and coverage of all of the wireless infrastructure the DOE has. So for an example use case of this would be a user facility efficiency, where let's say you have a large lab and you have tons of cabling for communication systems, but you can't run it for large distances. We could use this 5G network between the labs to allow communication between all of the actual facilities and the devices that are being used at the locations. So current activities with the project between the different labs is there was a commercial 4G CBRS trials in Colorado at Berkeley's labs and ANL. LBNL and ANL cellular tower research for small cell commercial models, and also open source 5G cores and commercial cloud implementations. And then Argonne, LBL, and NREL, and also in conjunction with California Poly, there was work with a wireless neural host MOCN system. However, I only work with the second one, and then basically making the 5G system and testing the test beds. So currently, we have a decent amount of stuff done with 4G and some 5G experimentation. And mainly, we're working on an open source 5G deployment model for these labs on a test bed to set up some sort of network in the preliminary stages. So right now we're using OAI. This is the standalone version. So we use the OAI core. We attempted to use SD core. It was just a little harder to set up with the hardware that we had. And we're using COTS-UIs and also evaluation test boards like the telemodems. All of our components for the systems, it's pretty standard for what comes off of the OAI documentation and also SRS documentation and SD core, things I recommend. So using standard USRPs along with some workstations to get everything working. Mainly in the 173 PRBs range is the research units we are picking because it seems to be the most stable. And we have a working test bed. And this was the main point, was just to show that we could get some private 5G system working, as there's a benefit in having an open model as opposed to paying for a private network to be used. So we were able to get about 240 megabit down speeds when we actually use the full bandwidth that the USRP X310s provide, with a actually very high uplink, about 11, which for being unbalanced isn't bad. Yep. Any questions?
So you mentioned sub-6 gigahertz spectrum. So what exact frequency is it? 3.5 gigahertz?
We're using the frequency spectrum 1. So FR1, that range. Inside FR1, yeah. And we tested at the very end with 100 megahertz bandwidth. Yes. Yes. So we tested up to band 78, and I think as low as band 48, because those we were just picking bands based on what our COTS-UI supports and what our telemodem supports. Telemodem we have seems to be most stable at band 78, so we've been more or less testing with that.
Hi, everybody. My name is Xinqi, and I just finished my master's study at University of Michigan, and next year will be my first year of PhD. So my research mainly focus on the core network slicing and the resource orchestration. And um, so I'm going to introduce the paper I recently published on ICC to briefly summarize my focus. So there are several challenges when you try to do the resource provisioning and placement of microservices and functions over the edge cloud system. So you have to find optimal placement method in order to because different microservices and different functions have different requirements, and each tiers has different resources capacity. So you have to manage all the aspect so that it can reach to the optimal placement. And secondly, we have to consider the multiple resource coupling effect. So what is the resource coupling effect is that you have multiple resources like network resources, you have computing resources, and these resources are actually contribute together to the overall performance of application that consists of many microservices or functions. Um, so based on these challenges, we have our system model. We can summarize that. First of all, we can the each computing tiers like multi-access edge computing server or cloud server can have a fixed amount of compute and network resources. So these are the two resources we are considered, and we have each application has several microservice functions, and they have um, a direct graph, like topologies. So first we have to went through specific functions, and then we can went through the next. And each microservices and functions is associated with a latency function and accuracy function. So these functions actually determine the performance of overall application. And the application can have an overlapping function, which means a shared function can serve multiple applications. So these are the system model. So based on the system model, we have a problem formulation. So we want to minimize the effective resource usage, and also we want to maximize the system allocation performance. So that's our objective function. And we have several constraints. And the first one, each functions or microservices can only be deployed on one tier only. And for each tiers, the compute and network resources allocated to the function or microservices cannot exceed the tier's resource capacity. And also, the function across the applications have the aggregated latency and accuracy within the threshold. So the latency, the accuracy, and the performance measurement we're considering. So we also consider the second step, which means that we also consider the effect of malicious application. So the first stage, we include the malicious factor, like there's a probability of an application being malicious, and when the malicious application has been detected and removed, we have to do the second stage, like reorchestrate the remaining resources for the remaining application, which is deemed to be benign. Um, so based on the problem formulation, we use an auto approximation algorithm to tackle the problem, which is mixed integer nonlinear programming for both stage. So this is our simulation setup, and we consider two applications has a shared function as a different topologies. Um, so this is the results. Like you can see the figure A and B. when you increase the probability of application 2 being malicious, you can see the resource usage for the both network and the computation usage is the application 1 has more resource usage as we increase the probability of application 2 being malicious. So on the contrary, you can see the figure C and D, and when you increase the probability 2 of being malicious, that the resource allocated to this application is diminished because we're indicating the potential malicious attack. And we also consider the trade-off between the latency analysis and accuracy. Like when you increase the probability of application 1 being malicious, and you can see there is a performance increase in terms of application 2, which is indicated by the red one. So the second stage is for the resource allocation. Like when you remove before the attack, the resource usage is 100%. Like you assign all the resources to the application which is deployed in the system. So once the application has been detected and removed, so the resource usage is actually decreased because there are other resources are not used because the malicious apps. After we implement the second stage, this is my the last slide, yeah. So once we implement the second step, which is reorchestration step, then there will be a slight recover compared to the stage after the attack, because why you cannot recover to 100% is because there is a constraint, which is the microservice and the function already deployed in the corresponding tiers. You cannot remove the microservices to other tiers during the second step. So this figure, like the second figure, shows the performance. Like when you at the beginning, the latency and accuracy is at this stage, and once the attack happens, the accuracy and latency performance actually decrease for the overall system. And once you perform the recovery process, there will be an increase of the overall system performance. Thank you.
How do you know whether an app is malicious or not? What information do you?
Yeah, that is the problem. That is not the layer we are considering, but we are. So that's you mean how to detect a malicious app, right?
Yeah. So your research starts after it has been detected that this is malicious.
No, my research starts the first. There are two stages. The first one, we assume each application has a probability of being malicious, and there's a factor there. So we include this factor and do the optimization. So how to detect the malicious app is not this work constraint, but we are considering. So that is the actual measurement. That's why we have to measure the real data, like the OAIC does. That's why I come here. Yeah.
So it's not necessarily. It's just even if the app is malicious, we have optimized for that factor anyway, because it's not you're looking for a malicious app. It's just you're assuming, like you were saying, that it could be anyways, and
yeah,
you're considering. Okay,
yeah, that's good. So there's a predefined, like this app. You assume the probability of this app could be malicious. You, for example, you assume that this probability is 0.9. So when the first stage of orchestration will allocate less resources to this app. So some kind of like a how can I say that? Like you assume based on some possibilities, like you using a circular slicing, you may detect some malicious data rate. You can assume that this app could be is likely to be malicious. Then when you do the resource orchestration stage, you will assume allocate less resources to this. And if finally it is has confirmed this is all malicious, you can remove this and you can do the second stage optimization, something like that. That's the problem. process.
Does the impact of I guess the potential impact of a malicious app affect the optimization, or do you just basically say if it's malicious, it doesn't necessarily matter what the damage could be?
Yes, the potential potential malicious could affect the resource allocation at the first stage. It's included in my first stage problem formulation.
Right, but I was talking. I meant like in terms of how much impact. Like say you've identified that there is a malicious impact.
Yeah.
Yeah.
That is how much would also affect how much resources would allocate to this. Because the probability. Like you really assume there's a 0.1 probability you could put malicious, so we're allocating more resources to this app. So yeah, it is corresponding with a level you deem could be malicious.
Thank you. Thank you.
Nathan.
All right, so hi, I'm Nathan. I'm an undergraduate student. I'm at George Mason University, but I'm working with Dr. Vijay Shah, who is in the NextG, or we're working in as part of the NextG Wireless Lab. Currently, they're moving from George Mason to NC State University. I'm in charge mostly of the ORAN software development and testbed development. So I'm going to talk about some of the closed loop developments that we've been working on and systems that we've been designing for Open RAN. So the main point is that we are designing systems that use the ORAN RAN Intelligent Controller, the RIC, and we're designing systems that can communicate between the RAN and the RIC. We have dynamic closed-loop control of ORAN networks, and we use AI-enabled examples to do this through XApps. So the first one we want to talk about is federal radar detection. So one of the things is spectrum sharing, where we are deciding that we would like to have certain traffic operate on the same frequency between two different services. So we essentially are looking at federal bands specifically, where we have, let's say, like a signal such as radar that needs to be prioritized as an incumbent signal, meaning that any other signal, like if we were to run 5G or LTE in there, it would have to be it would have to turn itself off or get out of the way of the connection when there is radar present. So we were looking into the CBRS band in 3.5 gigahertz, and the idea is that in the 3.5 gigahertz band there are spectrum sensors, and in these along the coastline there's sensors that are meant to actually that are specifically meant for the shipborne radar detection. But however, we can't actually deploy anything that such as a cell tower or base station in that area because those sensors are susceptible to any interference. So they can only detect the shipborne radar, and we can't put cell towers there. But our proposition through SenseORAN was that we would actually use the 5G base stations themselves as the way to detect radar. And doing this, it means that we can remove those spectrum sensors and we can alert the network way faster. So normally we would operate in under 1 minute, or we would have to be able to detect and act against radar in under 1 minute. But using an XApp in SenseORAN that uses object detection and can identify the radar through the channel, we find that we can actually operate in under 1 second. So that means that we have really good accuracy and we have really good performance. So we're able to improve that network, and we're able to deploy 5G along the coastline in that way. So we also have interference classification as another use case for the system. So essentially we are using the base station's received signals to identify network jamming. We can use a model that could identify the type of the interference if we'd like to, or focus on, or essentially just be able to act against any interference that's happening. So we investigated using spectrogram data and KPN. So essentially we can use images to look at the data, which is accurate, but the model takes a lot of performance and is slower. And there's also a security risk if you're able to decode those signals. So we also look into key performance metrics. So just looking at the blocking error rate and bit rate, which is faster and uses a lot less data, maybe like 20 bytes instead of 600 kilobytes for a spectrogram. but it's going to be less accurate. So there's a trade-off that we found between using spectrograms and KPMs. But once detected, the XApp, we can use that to mitigate some performance degradation. So in our case, we manipulated the modulation encoding scheme, and we were able to find that our error rate would go down by about 25% when we employed this solution. So this application we're going to be demonstrating tomorrow morning, and we're going to show you how we develop the system and how you can adapt it for your own needs. And then we also have millimeter wave beamforming. So we offer, essentially, we have the first millimeter wave network that uses Open RAN to dynamically control the network situation. So essentially, we have a transmitter and a receiver that are communicating with each other, and we're able to identify which beam is optimal for the receiver using the received signal strength. And the transmitter is connected to a beamforming client, and that client essentially operates as a way that can actually change the beams on the transmitter, but we determine which beams we're going to use by actually talking to an XApp in the RIC. And the RIC can decide, basically, in our case, we use a simple solution, getting the strength of the radar, getting the strength of the RSSI for that signal. And essentially, we can choose that best beam in that way. So that's what we do. So in conclusion, those are some examples for closed-loop dynamic control of the ORAN network. And a lot of this software, including the radar detection and the interference classification, has been released in OAIC and also open source in general. So we're also looking into things like real-time control that ran with EDRIC in collaboration with UC San Diego, and also automated unsupervised learning in the non-real-time RIC. Any questions? Yes.
So in the radar, so do you have to have a database that you know that the radar exists at this place, or you do it blindly?
So we are able to, essentially so what we did in that research was essentially we had one base station that was able to identify that there is a radar present, and it would do so in real time. So it would look at that, it would receive the signals from the RIC and then make a decision in the RAN side. But if we had multiple base stations and we need to make like an action across maybe multiple of the base stations, then we would need a database or some way to signal to everyone that there's radar. Yeah. Yes. Wait, for just in general or for the radar specifically? Oh, okay. So yeah, so you're talking about the latency in terms of like just like RAN to RIC communication and back and forth, or the actual applications? Oh, for the radar, like when we had like under a second, for example. Oh, the millimeter wave. Yeah, yeah. Sorry. So with the millimeter wave, what we were actually able to we were able to operate within a few milliseconds of each like beam switching. So being able to go from the RIC to the RAN. And because we didn't have this complicated algorithm, so it was mostly just the latency overhead of the network itself. So we're able to switch the beam really quickly as a result. Yeah. Yes. Oh, for the millimeter wave. No, we didn't actually do any synchronization or anything we just, because at least I think the synchronization, everything was managed by the beamforming client itself. And then it was just that the XApp would just determine what's the next beam that we should actually switch to whenever the system is ready to do so. Yeah. Thank you. Huh? Yeah, those are receivers, the evaluation kit. Yeah, yeah. And so we scale it up to 27 gigahertz through that. Yeah. Okay. You mean like how to just send data back and forth through millimeter wave?
Has its own Python-based thing. You just click
Yeah. But the USR, it's up to the USRP to decide what signal we send. So we weren't sending anything complicated like sine waves really. So. I mean, yeah, the main point of them is because you can configure how the beams are shooting, but you don't. It's not up to the servers to choose what type of data you're sending, right? You can choose like the polarization, like horizontal, vertical, but that's all like 5-layer stuff still. So yeah. Anyways, thank you. Yeah.
Hi everyone, I'm Ish from UC San Diego, and I just defended my thesis. I'm going to join RPI as an assistant professor, and happy to be here and talking to all of you. So here I will try to summarize some of my important work, mostly from the perspective of designing some interesting test beds that we have built at UC San Diego, and one part of it we will have a tutorial tomorrow on HDX. My research has been building millimeter wave testbeds and has been expanded into ORAN and a couple of other 5G networks. Here you can see one of the testbed that we have built in-house. We have a millimeter wave phased array, which is designed at UC San Diego with one of our colleague, Professor Gabriel Rabes. And then we took this phased array. This is the third generation of phased array. We started with like a simple chip design and antennas of phased array. Now it has become a commercial product that you can buy from the vendor. We have an FPGA to program it in real time, the clock module, the battery, and the SDR that we use Pluto as the smallest pocket SDR. We use high-end SDR using FPGAs and USRPs. So basically, we can do precise phase and gain control with 6 bits. We have 2 microseconds per beam scan, extremely fast using the FPGA. We have a 1000 size codebook which is inbuilt into the array, and it is ready with 5G new radio protocol. We use this testbed to develop a lot of applications, including reliable multi-beam forming, real-time mobility tracking, video streaming, and more recently in vehicular networking. We actually have demoed this testbed multiple times. This is one of the demo at San Diego Air Show, and you can see we have deployed our user side unit on a robot, and the base station is basically tracking the user. You can see the amplitude spectrum on the top, frequency spectrum on the bottom. It looks like a shape of a beam. The highest energy will kind of shows you the direction or the location of the device, and you can see that it is able to track in real time. So we are scanning hundreds of beams. All the hundreds of beams are plotted on the x-axis, and you can see which beam index gives the maximum strength, depends on the angle of the device. So this is one of the first university testbed. It is not developed by a company. We have all the algorithms and FPGA implemented to do it in real time, and we have control over any kind of programming we want to do. We can implement it here. Here is another testbed we built. We just not only acquire phased array. This is a new prototype of phased array that we built in our lab. Typical phased array has just a phase shifter. Here we explored a new element called two-time delay element. It actually not just creates a phase shift, but it also creates additional delay. What it helps is it can improve spectrum utilization in millimeter wave. We can essentially create multiple beams. These are not just standard multi-beams. Here we can split the beams across frequency. So frequency dependent beamforming. What you can do, you can send one frequency in one direction, another frequency in another direction. You can scan one frequency for beamforming, while another frequency is continuously beaming to serve user with a high throughput. Basically, if you have like 2 gigahertz bandwidth, you can fully utilize entire bandwidth in multiple directions at the same time. The key capability is each beam carries the same EIRP as the single beam would carry. So this is a testbed. We built basically the phase shifter board using the chips from Macom. We built the FPGA board. It's a RTX CMOD FPGA, and all the power and distribution modules are inbuilt. Here is another testbed. We have our millimeter wave radio testbed that we have already seen. We have integrated and synchronized with a radar in a similar 24 gigahertz band. And together we have camera and LiDAR as well. We have shown this integrated setup for joint communication and sensing, where we can look at the scene, understand the scene, and create beams without relying on extensive beam scan. A lot of application in terms of like by utilizing the bistatic nature of communication radio combined with monostatic nature of radar sensing, we can create next generation spectrum aware millimeter wave beamforming. Now, another aspect is on security. Here we have shown that these radars, which works in millimeter wave band, they are very vulnerable to spoofing attack. This is a device, it's a reflect array that we have built. What it can do, it can take the radar signal, modulate or change the signal in a way and radiate back towards the radar so that the radar hallucinates. It starts to see objects which are actually not there in the environment, or some objects which are there will disappear. Now imagine if you're driving and if someone hallucinates your radar and it kind of triggers automatic sudden braking or trying to change lane to as a response to this, and it may lead to accident, right? So we need to design the next generation sensing algorithm which need to ensure that they are not vulnerable to these kind of attacks. Right? This is one of the demonstration of the attacks that we did at IEEE SNP in 2023 last year. More recently, this is more relevant to what we are doing here. We have built a SRS-RAN based testbed. This is the HDIC testbed, and this part of there are multiple aspects of HDIC. One is it is a real-time testbed. It creates micro apps or D apps with less than millisecond latency. Here we are demonstrating that we can stream raw IQ samples from the SRS-RAN to our controller via HDIC, and we have shown using SRS-RAN 4G first, which has 2 antenna support, that we can create any kind of beam shapes. And for example, if there is a jammer, you can create a null towards the jammer. Okay? More recently, we have developed the latest version of SRS-RAN, which is 5G, which provides support for 4 antennas. And now, rather than streaming, let's say, raw IQ sample, we have access to the actual PUSCH channels into the controller. And once you have the channel, you can develop any kind of beamforming, beam nulling, other applications in sensing, for example, localization, and next generation security for using MIMO techniques. So these real-time controller will enhance the next generation MIMO and PI-layer techniques. More recently, we have been exploring and combining our research on millimeter wave and RAN intelligent controller. We are building a millimeter wave controller which can create real-time synchronized beamforming, which is compliant with protocol. And according to protocol, it will our FPGA, which does the beamforming, will be synchronized with the USRP so that we know exactly when to switch beam and which beam to switch. So these kind of testbed built in under university environment will help us enhance and understand, develop signal processing to further improve our understanding of these communication systems. Thank you.
Is there any correlation between the number of your real-time delays and the number of beams that you can have? Like, I guess, how does that scale? I guess, yeah, what's the scaling on that essentially? Or does that?
So number of beams that we have shown in my previous work, they are instantaneous. At the same time, they are radiated in different directions.
Right.
Right.
But so you were saying that you added the element of the real time.
Yeah. So those delays are nanosecond order. They're much faster than like million times faster than millisecond TTI. So the delay they create is a very small phase shift. Just that this phase shift is a function of frequency. Let's say if there is a delay tau, which is very small delay, will create a phase shift 2 pi f tau, right, for frequency f. Now the frequency is in gigahertz order. Let's say 30 gigahertz, 20 gigahertz, and inverse of gigahertz is nanosecond, right? So you can imagine there is a very small delay which can create a small phase shift, which will go from 0 to 2 pi, but it will be different at different antennas.
What are the security concerns in MIMO that aren't there?
So MIMO, we have explored one security vulnerability, which is jamming attacks, and MIMO has a way to create null towards the jamming direction so that you can protect your receiver from unintentional interference or jammer. Other other kind of security vulnerability you can think of in more generic term, like which comes with the use of ORAN itself. Like since we are sending the raw channel back to the controller, if someone can intercept these channels, they can develop and control in a way that maybe they can maximize the signal towards the jammer instead of minimizing it. So how can you protect? It come under the standard umbrella of like how can you avoid interjection of the signal and avoid bad actor to get access to these important resources from the LAN.
Gotcha. Yeah, I just didn't know if MIMO had its own novel threat vector instead of like because jamming works with any type of, right? And the ORAN threat is very real on many different levels. But yeah, of course, jamming is a threat. Right? Jamming is a threat.
Jamming is a threat, and using MIMO, we can develop an XTAB which can help us to avoid
mitigate.
Mitigate.